Okay, here we go with video 2 for chapter 5. So the next thing we want to look at is back to that line spectrum. If we had a lamp with hydrogen in it and we run electricity through it and then we peek through and look at the spectrum of light it emits, we would see 4 lines. Now this is photoshopped because I wanted to make sure everybody could see all the different colors, but in reality, some people see this red line really well, but not the purple line on the far left. And sometimes other people see the opposite. I see in the purple region really well, but I don't see the red very well. So I did Photoshop this. When we look at this for real in class, it is going to look a little bit different. But what's interesting about this is that these 4 colors of light are able to be calculated using Bohr's model of the atom and some math that was developed by other scientists at the time. So the way that it works is basically to go from the highest energy level that hydrogen can have, the highest excited state, is the 6th energy level, and so this is the biggest gap. If you fall from 6th to 1st, that's the highest energy. And that means that in the visible spectrum anyways, the highest energy color is red. So when an electron goes from the 6th orbit down to the 1st orbit, it creates a beam of red light. When it falls from the 5th to the 1st, you get this beam of blue light. From the 4th to the 1st, you get this like purple color, and from the 3rd to the 1st, you get this brighter purple. It's close to the UV spectrum, actually. Now, there are other lines. There are other energies out past 700 nanometers and before 400 nanometers. So lower energy and higher energy, respectively. But we can't see them with our eyes, even with instruments. We can't perceive UV or infrared light. So the other transitions, such as between, say, the 2nd and 1st orbits, or maybe the 7th down to the 1st, we can't see any of those. We can only see the ones that happen to fall in the 400 nanometer to 700 nanometer range. So these are collectively called the line spectrum of an element. If I have 2 different line spectrum, I would call it line spectra. So it's a Latin word. We put an A on the end to make it plural. So Bohr's theory completely correctly calculates these exact wavelengths. But if we try to look at even a slightly more complicated element like helium, which instead of 1 electron and 1 proton is 2 electrons and 2 protons, Bohr's model cannot calculate anything about that. All of the numbers don't match up with what we observe. So there must be something incomplete about Bohr's model. Okay, so we're going to have to explore that. Now, his model did get something right. He correctly found that electrons can really only exist in certain places, and he called those places orbits. You can think of it like a pair of stairs, set of stairs. So here's one orbital, here's another orbital, there's another one, there's another one. The electrons are allowed to sit on top of the steps, but they are not allowed to exist in between, which is very different from the real world. This is what we would think of as the macro world. You can exist anywhere along the stoop that you want to be because people can travel through space without any real restrictions about where they can kind of exist. Electrons, because they are quantum particles, don't have that luxury. They have to be in certain places and cannot be in other places ever. So we think of that as sort of a staircase, where each level of the staircase represents an orbit that an electron can be in. So Bohr got that part right, and that was a really revolutionary idea because we had never considered that tiny particles might behave in a different way than sort of regular matter. In order to explain the helium atom, we had to develop a more refined model of the Bohr model of the atom. So two guys come along, Louis de Broglie and Erwin Schrödinger. And Schrödinger was actually a statistician, so he was interested in statistics, which is really all about probabilities. And he said, okay, what if we take the math that I already understand and I apply it to electrons? So rather than Bohr's model, which is the one shown here on the left, where electrons kind of zoom in certain places, Schrödinger said, you know what, I actually think what happens is that electrons mostly exist very close to the nucleus. And so I'm going to create this picture, which is a 90% probability diagram. And what that means is each dot sort of represents the probability of an electron being in that spot roughly 90% of the time. One of the cool things about this theory is that it implies that there's about 10% of the time where the electrons are allowed to be much farther from the nucleus, outside of this little sphere here. So that means that, in theory, there's no limitation to how far away an electron can be from the center of its atom. My electron might be on the moon right now, or maybe it's taken a vacation in Florida, which is much warmer than here currently. There's no way to say that's not true. The electron can be kind of anywhere it wants to go, mostly. But we are much more likely to find the electrons clustered around the center of an atom. Okay. Now, when we think about probabilities, we get one energy level where the electrons are very, very close to the center. So we call that the ground sort of lowest energy state. When we're thinking about the hydrogen atom, the lowest energy state is when the principal quantum number, which we abbreviate as n, equals 1. There are other variables that represent all the different parameters to characterize an electron. But the most important one to understand is the basic energy level is 1. And this correlates with the period number on your periodic table. So if you find hydrogen and you look at your periodic table there, right next to it on the left-hand side where the periods are numbered, the number 1 appears. That tells you that the energy level of hydrogen is 1. If you go down to the second period, energy level 2, everything in that period, everything going across the periodic table in period 2, has an energy level n equals 2. At that point, you have more than just the sphere that we just saw in Schrödinger's diagram. You also get something called p orbitals, which look like 3 bow ties that are kind of stuck together. So there's 3 shapes in a p orbital and a p energy level. And there are regions in space where the electrons are not allowed to be. That connected with Bohr's model of the atom, because Bohr said electrons teleport from one place to the next, but they don't exist in between, and Schrödinger's equations calculated the same thing once you get down to period 2. So that helped to explain some of the strange math we saw with Bohr's model. Okay. So it's important to remember what a group is and what a period is, because of course the energy levels are numbered down the side by the period. The group levels actually tell us a couple of things. They tell us which orbital they fall into, which means the shape of the electrons, and they tell us the total number of electrons. So we sort of have to pay attention to both of these parameters as we go through.